Hello, hello. All right, the mic is working. I've had to take a couple notes before I come into my talk after hearing all the great conversations that have taken place at this event. So before I start, I want to thank the organizers. This is amazing. Bringing the right people together to talk about confidential compute. What a great opportunity. And to see everybody in person is nice. After a couple years of working in the Confidential Compute Consortium and not having to see anybody, it's really nice to see people in person. I think when I think about confidential compute and think about ARM's position and what we're doing here, I think we offer something unique. And that comes from the fact that our partners are developing solutions that are in many verticals, from IoT to client to automotive, and of course the hyperscaler environment. So when we think about security, we're really thinking about how does this work across all of these various landscapes, the whole landscape, right? All of these different verticals. And I think that gives us a very unique approach to how we consider security. In one of my discussions earlier today with Kurt from the Linux Foundation, we were talking about the security aspects of confidential compute. And one way to rationalize what is happening is we're completing the circle now with confidential compute. We had protection for data at rest. We had protection for data in transit. And now with confidential compute, we got protection of data in use. And that really enables us to offer end-to-end security, where you're now completely in charge of your data, which I think is also a very unique way of looking at the situation, it's the right way to look at it, right? This is really closing the loop. A lot of discussions around the regulatory requirements, and ARM is very much aware of this, being part of the Confidential Compute Consortium. I think that's an environment where we can really tackle that challenge. So I think that's really cool. And with that, I'll start the presentation. Okay, so what we have prepared for today is really going to be broken down into 3 different topics. The first one, we're going to look at the development projects that we're driving that start from the hardware and build up to create solutions that eventually get to a point where it doesn't matter what you're running on. It should be transparent that you're running in a confidential compute environment. Right after we finish that build up, we're going to look at how attestation cuts a path across all of these different layers and offers a unique solution, right? It's something that needs to be dealt with holistically, and it's something that, again, I think is very important to do as a consortium, as a group. We have to figure out how we make attestation work across the board and make that transparent for the end users. And then the third part of it is going to be looking at some of the examples of projects we do in a community that are higher level up, allow us to validate some of the assumptions that we're making, the work that we're doing, and also our way to collaborate and provide reference designs. Okay, this is as far down in the hardware space as I'm going to go into. ARM RME is the extension that was added to ARM v9 to enable the environment that creates confidential compute on ARM. What RME does is it introduces 2 security states. At the bottom, you can see the root state that's been added, and also the realm state. And the blocks that are listed in color here were there in ARM v8 in the previous generation. One of the exceptions to, or one of the areas that falls kind of in the gray space is the monitor that you're seeing now in the root space used to be under the secure environment. So that now has moved down. It's in its own security state. And that's where the dynamic memory allocation takes place. Being able to allocate more memory to your secure environment or to the realms environment, which is the new security state that was added. Something to notice in this diagram as well is that the realm environments sit above the hypervisor in the host when it comes to resource allocation. But when you consider the data and the protection of the execution environment, it's in its own separate state. And that's a distinction. If you think about how we go from secure, non-secure, and then extend into realm, there's a distinction between the realm environment and the secure environment. That's one of the key differences there. Now, we're not going to stop with enabling this new security states, making that available to our silicon partners and walking away. We're also investing higher up in the stack to enable the software. Everything we do to enable the software that enables a confidential compute environment is in the open. This is an example. This is the first layer that touches the hardware. Trustedfirmware.org, an open source organization where we had already investments in security. We've extended some of the projects. So TFA Monitor is the extension of the TFA project, which is already part of Trusted Firmware, now can support the monitor features. TFRMM, when you think about the hypervisor that's managing the resources in the host, in the non-secure world, that really needs to be broken apart. You need some of that functionality to move into the secure environment to manage the instructions. That's been added to a new project called TFRMM in trustedfirmware.org. And then the third piece listed down below, and it's separate from the A-class processor, where all of this, these new instructions were added, is a microcontroller that serves as the root of trust of your system. So in case you didn't know, when a partner takes the A-class license and builds a solution, they can get the microcontroller there as well as part of the package. And that microcontroller is part of their solution. So you're separating your root of trust, and that's a much better implementation. And all of the code that enables that is part of the TFM in the RSS instructions that were added in that project. Now, going one step higher, TFRMM exposes two ABIs, one on the host side, the non-secure side, and one in the secure side. In order for those instructions to be picked up, we've introduced patches to KVM and Linux host. Those patches have been made available, are hopefully going to get picked up soon and pushed upstream. And they enable the communication between the realm and the non-secure world, anything that has to do with the setup of the environment. And then on the RSI side, the same idea, right? The exposure of those commands in EDK2 and in your Linux OS have also been added to those projects, and they're available as well. So again, everything that we're doing here is really building up from the changes that are done in the hardware, exposing that to the low-level firmware, exposing that again to reference designs in KVM and Linux host. Everything is open source. If there's a need for this to be ported to a different project, the instructions are there. You can follow these blueprints, or if these implementation work for your application, you can just pick it up and run with it. Now, to enable development, enable simulation environments, testing, we have different platforms available. And what we're doing is we're taking all the components that we've put together, putting them into a software stack, and then validating that on FVP models. We've got two FVP models available. One is the A-class processor on its own, and allows you to work in a smaller environment if you're focused on applications that are running in a VM. And for the cases where you need to test out the attestation flow and the full system flow, there's another FVP that includes that little microprocessor, the RSS implementation, and that gives you the full picture, everything you need to validate the entire flow. So at this point, I'm going to pass it over to Thomas to go into the details of attestation. He's going to talk about some of the projects that we're running in open source that are a bit higher level. And then I'll come back at the end of the session to close it off.
Right. You can hear me, yes? How do you switch? This one. Okay, as you've probably heard multiple times today, attestation is a core component in every confidential compute flow. And that by definition, we have heard from Mike this morning that a CC environment must be able to attest itself, or it can be called a CC environment, basically. So quick refresher on attestation, what is it? It's a very powerful authentication primitive that can convey the security state of the workload's TCB alongside the identity of the computing environment. It's used in the context of a secure distributed computation, which we have lots of use cases, as we have seen today. And in that context, it enables encoding very precise authorization policies, and therefore encode the contracts between the parties that participate into this secure computation, distributed computation. And this ability to build these software contracts among these different elements of the computation is what makes it a fundamental building block for all the use cases that fit this pattern. And since it's so pervasive, we need to make sure that it is as smooth as possible. All the flows that involve attestation must be as smooth as possible. And at ARM in particular, where, as Marc was saying, we have very many different environments that we need to take care of, IoT and server and mobile and automotive and whatnot. It's very critical for us as a company to make sure that we have a uniform attestation workflow across all verticals. At the same time, we recognize that fragmentation is, in some sense, unavoidable for legacy and other reasons. And so we need to make sure that fragmentation can be taken care of, can be absorbed. So we need, on one side, standardization for the common case, and on the other side, we need shock absorbers for the exceptions. And we think that this is not just ARM, it aligns very well with the wider ecosystem where we have this, dual situation. And to these goals, we work with standardization bodies to create these uniform interfaces. In particular, we're involved actively with the IETF and the RAS working group and the TCG. But we also engage with in the industry consortia like CCC, where we are very active, and we want to be there to gather use cases, to discuss in an open and cooperative environment the important things, right? And we try to create to seek for harmonization options. And one luminous example of this is the work we are doing in attestation, SIG and CCC, about attested TLS. And the third prong is providing open source software to enable end users as well as our partners to take advantage of confidential computing. And I'll go through a few of such open source projects now that we either started or we contribute to. One is Project Verizon, of which I'm a tech lead, so I know a bit about this. So if we've said attestation is central to confidential computing, then verification of attestation is central to all attestation flows. So it's at the core of the core, right? So there's where Verizon sits. So we started this project to provide building blocks, componentry, to assemble a fully fledged verifier. But also, we did more than that. We are also providing tooling for the supply chain, for relying parties, for verifier owners. So basically all the interfaces that you can see there are taken care of by Verizon in a way or another. And it's been 1 year since this has been adopted by the Confidential Computing Consortium. And we started very small with a team of 4 in ARM. And we are, building a community, which is slowly but steadily growing. And we have a few integrations already, which have been fun to work with. We're looking for more, so in fact, if you have one use case that would fit this picture here, please come and talk to me. I'm super happy to hear from you. We are using Verizon also as a driver for the standardization part of the main interfaces that you can see there. And this has proved to be super useful as a feedback device into the standardization process. So we have various standards that we are providing code for at those interfaces, and while implementing and playing with those, and we have useful feedback to the standardization process. And it also works as a shock absorber because it has a software architecture which has a very well-defined processing pipeline, but it allows at well-defined points the injection of user-provided code to sort of smooth out the diversities, take care of diversity. Yeah, so as I said, please come and talk to me if you think you have anything to do with this. Another project is Parsec. Parsec is a project in the CNCF, donated to the CNCF, is in sandbox state at the moment. It provides abstractions for security services in general. And in particular, we are, at this point in time, we're extending it to provide an abstract interface to different root of trusts. So strategically is one of these shock absorbers that hides basically the low-level fragmentation from either the application developer or the system integrator. And we also have a couple of projects that sits a bit higher in the stack. One is Veracruz, yes. This is another project that we started at ARM, in ARM Research, and then we donated to CCC. And it is a framework to experiment with secure multi-party computations between the usual mutually distrusting parties. And we use a T and attestation and remote attestation to create this sort of neutral ground where the computation can happen. Veracruz uses WebAssembly to create the sandbox where you can run your workloads. And the use cases are those that you have already heard about, privacy preserving, collaborative ML, secret auctions, elections, poll, whatever. The fourth one is Coco, yeah. So we also want you to be able to build your and deploy your containerized confidential app on top of ARM CCA, as well as other CC provider, and with simple lift and shift. And for that, we joined the Confidential Container project, which is a CNCF sandbox project. And for now, we've managed to bring up the kata containers in a Realm VM, so in the ARM CCA isolate primitive, using QEMU and the software model that Marc was talking about, the FVP. And we have ongoing activities at the moment and plans to fully enable Coco on ARM CCA. That includes, adding the Coco runtime and attestation and the Cube integration to the thing. And yeah, this concludes the overview of our open source efforts in the confidential compute world. And the message is we really want to hear from you and we really want to collaborate with you. So yeah, if you happen to have use cases, come back and talk to us. But I will leave a more articulate thing to Marc.
I think you've said it well, right? So we're ready to take questions at this point, but if you do have an interest to go deeper into some of the topics we've talked about, we recently delivered a webinar at the Confidential Compute Consortium, and that's that's been recorded. It's on the website. It goes into great detail. So it talks about RME, it talks about CCA, it talks about the enablement pieces, and a little bit about our roadmap. So that's a great place to start if you're interested in more details on the topic. You can join us in the communities. And yeah, we're ready to take questions. And I see a few hands up. Perfect.
Can you talk a bit about the endorsers, the role of endorsers in the attestation architecture? At the end of the day, attestation tells me reliably who you are, but doesn't tell me why should I trust you. Are you EL certified, PSA certified, CESIP, and so on and so forth?
Did you understand the question? I think the question is around attestation. And
Yes, endorsements, but
Endorsers, what's the role of endorsers? How do I get...
Endorsers is the supply chain entity that feeds the endorsements and ref values into the verifier so that the verifier can complete the verification process. So it can verify the attestation assertion using the cryptographic material that is fed into the thing, as well as matching the ref values against the evidence that comes in, right, to make sure that the identity is effectively what is expected. The desired state of the attester, of the attester's TCB. Yeah, sorry.
Well, a quick follow-up on that question.
Yeah.
If you have the endorsers and the verifier, and if you have other, bits that are coming into the attestation process, how do you know the identity of the sources from which these?
There need to be a trust relationship that's pre-established. So you have, all the endorsements are assigned cryptographically, and therefore, the identities of the signers are known in advance to the verifier.
I see. So there is no scheme to just have, because you would need a global namespace, right, to enable everybody to contribute and have a dynamic, automated mechanism. What you're saying is that everything needs to be manually configured, right, to be able to feed into that attestation process.
Which could be a very painful process if you have to know every single key.
Yeah, which I think is related to this, is that you need to know where you get an attestation, right, and you say, I'm going to verify it, but you need to verify it against a list of authorized things.
Yeah.
So. Right.
Mm-hmm. Right. But yeah, you need
So the good news
trust
is that
anchors of some sort. Sorry. Yeah.
The Verizon project is an open source project in the Confidential Compute Consortium, and there are regular discussions. I believe you have weekly calls, right, Thomas?
Yeah.
On the topic
on
that take place. So if you do have more in-depth questions, I'm sure
absolutely, yes. So I forgot to mention
answers for these questions. We can talk at the table.
Excellent point. Yes.
Yeah. So thanks for the talk. I just had a question because at the beginning you showed the software stack that you guys have. I guess you have fast models to test all of this on the FEP.
Yeah.
Are you aware of any hardware coming up that we can use to see like the real performance of this and that we can try?
Yeah, that's a really good question. Clearly, everybody wants the hardware in their hands. ARM has released the architecture to the silicon providers, our partners, at the beginning of this year. So they are in the process now of preparing for tape out, preparing for bringing these solutions to the market. So we're still a little bit early. It's coming. Our goal at this point is to ensure that everything that we've provided and that it's validated and that it's proven out, and also that we get a head start in enabling all the software bits so that when these silicon solutions come to market, they're ready to use. Yep.
So just a question, you mentioned the Parsec project, and I would like to understand better how it can be used for creating the attestation for trusted execution environments, or what would you suggest from the stack you mentioned to be the best thing to use for creating the attestation, for example, for SEV or some other trusted execution environments?
Okay, so this is new for us. So we have just started creating this abstraction. As I said, this is an experimental feature that we've added to the project recently in the context of attested TLS prototype that we're doing in the CCC SIG, attestation SIG. And, we have created the abstraction and two instances of ROTs. One is TPM based and another one is CCA based. I wouldn't know how to.
I think that slide had a little pop-up on it that said, come to the talk at 4:30. Our colleague Nathaniel, or not Nathaniel, Nathaniel's here. Matthias is going to deliver a talk that extends that slide, talks about Parsec, its role, and the attested TLS proposal that we have put together.
But could you rephrase your question in order to?
You mentioned the Parsec, and I wonder how the Parsec can be used, the libraries that you mentioned, and then if not, what else can be used from that stack of the technologies that can be used to automate that process and make it easy?
To abstract the ROT?
The whole attestation process, I would say, what we are attesting, so how we are doing the measurements and where we are sending the attestation, what kind of format of attestation you are suggesting. Do we have libraries for that? If we are creating an enclave agent to do the attestation, how do we exchange the cryptographic material and all of this?
Right. So, great. We are building standardized interfaces for the endorsement and ref values, so that you can have this format is called CORIM, been developed in TCG first and now brought to the ATF for standardization there. So we have this cross SDO effort on that set of interfaces. On the attester to verifier path, that's where fragmentation exists. So you cannot pick and choose whatever you want. You need to, whatever your ROT provides is what you're going to use and you need to consume, right? There's no choice there. So effectively, the best that we can do is to make this abstraction for you and make it possible for you to forget about what the low-level details are and resolve the complexity by joining the verifier and the attester, right? And leaving the core attester and leaving the application layer out of the equation, right? So creating, for example, one of the devices we use is this encap mechanism that is homogeneous and can transport every single possible attestation format, right? So the application only sees this opaque blob, right? It's just always the same shape and fires it up to the verifier, and the verifier resolves the complexity, right? And then on the path back to the relying party, we are standardizing the attestation result format. So it's a way to actually communicate in an abstract way, right? But still rich enough for you to build authorization policies that are meaningful, right? And it is a thing that is based on another standards we're developing in the RATS working group, which is called R4C, which is basically it sort of hides the complexity of the attester and sort of creates an abstraction along some of the dimensions, trust dimensions that are important. So for example, the fact that this is a CC environment, this has encrypted memory or not, or in terms of feature. And then you have a scoring system that is standardized, and that is the sort of core semantic that we transport downstream to the relying party. This is based on JOT, and therefore someone talked about OPA policies and integrates fantastically with OPA, because OPA can consume JOTs, and not only from a point of view of parsing the claim set, but also from the point of view of verifying the actual crypto envelope. So, in 4 lines of Rego, we can actually build a complete relying party, right? So, I don't know, I'm a bit rambling, but...
Clearly, Thomas is very passionate about attestation, I think. Thank you. Thanks, everyone.
Cool.